Hi to everybody. So in this work we try to abstract the quantum entanglement. So before starting with the abstract domain part of the talk, what is entanglement? But first, what is a qubit? You know that since we are in quantum computation, the smallest information unit usually is a qubit. That from our point of view, the only thing that we have to know is that in general this qubit could be represented with a two-dimensional vector, with a vector in a two-dimensional Hilbert space. And so since we have in a two-dimensional Hilbert space, we need two bases that usually are 0 and 1, so these two vectors. And since we are in a Hilbert space, it's a complex space, so we need two complex numbers, and our state will be the linear combination between the two bases. And this is how we can represent a qubit. But the entanglement is a phenomenon that happens when we are working with more than one qubit. So let's see how we represent system in which there are more than one qubit. Let's consider, for example, two qubit. Two qubit, the state of two qubit states in a space that can be made composing the space of the single qubit. So in this case, we have two qubit, we have the space of the two single qubit, and we put together the space using the tensor product. So in this way, we obtain a four-dimensional Hilbert space. So we have four bases, and the state of these two qubit will be a linear combination of these bases. So a four-dimensional vectors. Similar, if we have three qubit, we will have the composition via tensor product of the three spaces, so 8 dimension, 8 bases, and the vector will be a 8-dimension vector that corresponds to a linear combination of the 8 bases. So you see that when we want to obtain a bigger space, we compose the smallest space that composes the bigger one using the tensor product. So for example, if you have these two qubit, their state is a state in a space that can be obtained composing these two single state, but the global state can be expressed in this way. So if you have two qubit, can we express the state of these two qubit composing using the tensor product the single state of the qubit? The answer is sometimes. In particular, when this happens, it means that these two qubit are separable. So basically, the state of the first qubit and the second qubit are independent. So the global state is a composition of the two single states. This is just like a classical state in which if we have 5 bit, the state of this 5 bit is the composition of the 5 single state. When we cannot write the state in this way, it means that the two qubit form basically a unique state. So this means that the state of the system, that in this case is composed by two qubit, cannot be described separately. Because basically these two qubit that can be two particles, two quantum particles, basically their state are linked, so entangled, and they cannot be separated. But what does this mean? Let's see first with some example. For example, if you have this state, it's two qubit that form this state, so for a uniform superposition of the four bases, we can actually write this state using the tensor product. So this is the state of the first qubit, this is the state of the second qubit. In fact, this state corresponds to a state in which the two qubit are separable. In fact, if, for example, we do some operation to the first qubit, just like a measurement, we can obtain different result since the first qubit is in superposition, but in both cases, the second qubit is still 0 plus 1. In fact, you see basically when you measure 0, it's like we select this part of the state. When the measurement returns 0, it's like we choose that this part remain. Of course, it's a probabilistic thing, but we can say that basically this part of the state remain, and you see that here is 0 plus 1, the second one. Similar in the other case, the first result 1, so we keep only this part of the state, and the second is still 0 plus 1. The things are different if we consider an entangled state. This is an entangled state. How we can see that? We can see that. First, we can see that we cannot we cannot separate the state of these two qubits, because basically we cannot say that the first qubit is 0 plus 1 as before, because basically the first qubit is 0 only when the second is 0, and similar with the one case. In fact, we cannot write this state using the tensor product as a composition of two states. In fact, if we measure the first qubit, again we have two possible results, but if the measurement returns 0, we have basically choose the first part of the state. So also the second is 0. The same happens when this one. And this happens when we do a measurement, but can happen also with other operation. For example, if we have this state, we apply the Z operation, that is a simple operation that changes the sign of the amplitude of 1. So if we have alpha plus beta, it's become alpha minus beta. We obtain this state in which we have changed the sign of the first, but we have also changed the sign of the second. So since these two qubits are entangled, it's like they form a unique state. So every time we work on one of the two qubits, we are actually working on the pair, because they are not separable anymore. For this reason, it's important to reason about entanglement, because if you think about a quantum program in which we have quantum variable and some variable are entanglement, if you write Z Q0, we are working on Q0, but we are also altering all the other variables that are entangled with Q0. So it's important to understand which are the group of entangled variables in order to proper model which are the variables that are altered every time that we do some operation. So what we want in our domain, we want that if we have some qubit in some state, we want some absolute representation that work on the set of qubit and told us which are the set of qubit that are potentially entangled. So for example, if in this case, you know that every time we work on Q0, we also alter Q1, and every time that we work on Q4, we do not alter the other one, for example. And this is what we want to obtain with our absolute domain. So first we need to define some property. The first property that we define is the separability that we already seen before. We generalize this property. We see before the separability with the case of two qubit. In general, if we have a set of qubit and two qubit that stay in this set, we say that these two qubit are separable if basically we can break the state in two states where, for example, X is here and Y is here. Okay? And when this doesn't happen, we say that these two qubits are inseparable. In this case, we don't speak of entanglement, but we speak about inseparability, because when we have two qubits, being not separable is the same as being entanglement. When we work in a multi-qubit system, it's a bit more complicated, because the entanglement in a multi-qubit system not always looks to the global situation, that's what we are looking here, but it also looks to the single binary, to all the relations that there are in the subsystem, basically, so which are the relation between the pair, between the group of three, and so on. So for this reason, we use the word inseparable to refer to the concept that we don't want to model all the possible relation in the subset, but only understand if we can divide or not two variables. There are more detail about this in the paper. So, for example, if you have this state that we can write in this way, it means that we can separate one from the rest of the state. So this means that D is separable from A, B, C, but A, B are not separable, like B with C and C with A. So how we represent this, the separability or inseparability of this state, using a partition on the global of the set of the qubits. So in this case, A, B, C are together since they are not separable, and these in another set because it's separable from the other one. Here there are some other examples. For example, in this case, we can separate A and B from CD, so we can represent the state in this way. And similar in the other case, we can represent the separability in this other way. So apparently, we have obtained what we want, because given a state, we have the set of qubits that are separable. But is this enough to proper reasoning about entanglement? Let's see this example. In this case, we have two entangled states with two qubits. We note that this state is not the one that we have seen before, because basically there are a minus sign, and this minus makes this state entanglement, while in the previous case we have a plus, so we can write in this way. In this way, we cannot write this state as a composition of two separate states, because there is a relative phase here, that is the minus sign, that don't allow us to break the state. So these two states are entangled, and from the separability point of view, they are the same state. Like in the abstract domain, they are the same state, since A and B are not separable. But let's see what happens if we apply a measurement to these two states. For example, if you measure the first qubit, in the first case, we can obtain 0, 1, of course, because it is in superposition. And in the first case, the second qubit, according to the result of the measurement, may be 0 plus 1 if you measure 0, because we choose these two if you measure 0, or 0 minus 1, because we choose these other two. So if we measure A, we alter B, because B will be one of them with a different relative phase, but B is still in superposition. In the other case, if we measure A, like we have seen before, the B will be 0 or 1, but you see that in this case, B will collapse to a classical state, because basically this is always 0 or always 1. So this is a quantum state, but it is in real classical, because there is no superposition of value here. Instead, here we have a superposition of value. So you see that the relation between A and B in this state and in that other state is different. Because when we do a measurement, basically when we do a measurement here, we causes more damage, because we make also the other qubit collapse to a classical state. And why this is interesting? This property is interesting because it implies another things that happen when we apply a control knot operation, that is a knot. So we negate B if A is 1. And if we apply this operation to the first one, we obtain another entangled state. Because basically we do nothing here. In this case, this is 1, so this becomes 1. We do nothing here, this becomes 0. In fact, this is 1, 1, and this is 1, 0. Instead, in the second case, if we apply C naught AB, we obtain this state, because in this case we do nothing. In this case we negate B, so it's become 1, 0. So you see that in this case, when there is this direct relation between the qubit, with a simple operation, that is a C naught, it's a simple gate, we have nullified the entanglement between the qubit. So this is why this strongest link that happen in this case is important for our domain, because thanks to this, because if we are able to track this property, when we are also able to understand when some operation can nullify the entanglement. And this is why representing only the separability, it's not enough. But we need also to represent this other property to get more precision. So we define this property as a direct inseparability, because it's like a direct link between the qubit. And basically we say that two qubits are directly inseparable if, when we measure one, also the other collapse to the base state, as we have seen here, as we have seen here. So, for example, if you take the first part of the state of the previous example, we can apply different measurement, and you see that if you measure A, we can obtain two results in which you see that here C is in superposition, is 0 plus 1, but B is always 0 or always 1. The same if you measure B, A is always, okay, this is a typo, should be 0. A is always 0 or always 1. Instead, if you measure C, A and B are in superposition. So with this example, we also see that this property is also transitive, because if we measure A, B collapses to a base state. If we measure B, A collapses to a base state. And so in this case, we obtain that the direct inseparability in this state happen between A and B, but not with C. So if we want, so we know that I and B are the inseparable, and if you want to represent this property, also in this case, we may use a partition of the set of qubits. So this say that the qubits that are in the same set are the ones that are the inseparable. And here we can see with the C0 that if we make a C0 between two qubits in the same set, we nullify the entanglement. Instead, if we do with two qubits in different sets, we basically obtain another entangled state. So, given a quantum state, what we want to represent is the separability, in this case A, B, C, and D, because there is a tensor product, and the direct inseparability. In this case, since to be direct inseparability, you must be entangled, so you must be inseparable. D is separable from the other, so it's still not the inseparable with nothing. And the three state ABC, the three qubit ABC, that here are all together. If we consider the direct inseparability, as we've seen before, we have A and B that are direct inseparable, and C that is not direct inseparable with them. So to represent these two partitions together, we use this notation, which basically represents the smaller one, that is the direct inseparability, and we add some index to know which are the sets to join to obtain the set of separable qubits. So more formally, our abstract state will be a set of pair where the first element is a subset of the qubit and the second element is an index, and in particular all the first set together must form a partition of the original set of the qubit. And we use this letter to indicate the domain, that is the set is a subset of the set of the pair between subset and the pair of subset and the integer. So to complete the domain, we need to define an order in this domain. In particular, with this order, we want to represent the fact that we need to overestimate the inseparability, since our goal is saying which are the variables that may be entangled. So in this order, we overestimate the entanglement. But at the same time, we need to underestimate the direct inseparability, because being direct inseparable implies some effect. So if we want to be sound, when we apply this effect, we need to underestimate this relation. So this inseparability must be ordered in this way, and the direct inseparability in the inverse sense. And the final order, we can define the order in which we respect these both directions. So you see that when we go up, the set of inseparable variables become larger. You see that here there is always 0, so it corresponds to this set if we join the 0. But the single set that correspond to direct inseparability are smaller. So concluding, now we have the abstract domain with an order in it. We have the concrete domain that, in this case, in our case, is made by sets of vector in the Hilbert space of the qubit. We have defined a concretization function that goes from the abstract domain to the concrete one. In particular, this concretization function build the set of the state in which we can separate the state according to the bigger partition, and in which all the qubits that are inseparable are actually inseparable in the state. So I mean, this means that we build the concretization correspond to all the states that are properly abstracted by the abstract state. And then, since these two relations, the inseparability and separability relation, are actually an equivalence relation because they are both transitive, symmetric, and reflexive, we have a since they are equivalence relation, we know that we can build a Galois connection between these two domains. We have the concretization function, and we can use the concretization function to define the abstraction function. If you are more detail in the paper about the construction of these two functions. And so concluding, what we have done with this domain is we have introduced a domain that allows us to reason about entanglement. In particular, our goal was to bring in this domain enough information to capture when the entanglement may be nullified. So in this case, so as we have seen before, if we simply represent the entanglement, we cannot say if an operation nullifies the entanglement. But if we add the information of the direct inseparability, we know when an operation like a C0 nullifies the entanglement. So in this case, with the richer domain, we know that with this operation, we pass from the state in which A and B are inseparable and direct inseparable to the state in which A and B are separable. And we have built a domain in order to build an analysis, in fact, as a continuation of this work that was a future work in the paper, but now is more an actual work. We build a static analysis that fully employ this domain. So basically, we have added also another element to this domain that it is some label to represent the state of the qubit, and then we have defined all the abstract semantics to properly analyze the entanglement. Thank you.
Are there questions for Nicola?
Okay, just trying to understand precisely. So it's not closed under simplifications, right? So you might have two Hadamard gates after each other that correspond to the identity. And if you analyze the first system, you would get that they are entangled, if I understand.
Yeah, I mean, with the Hadamard gate, you cannot. I mean, with the Hadamard gate, you create the superposition. Like with basically, the idea is we want to track when there are some gates that might nullify the entanglement. Of course, with some approximation, because basically everything is reversible, but you cannot actually represent everything. So this is the idea. I mean, I have a slide with a sort of an example. Okay, this is an example. To actually complete the analysis, you also need some label. This is come from the paper, so we use also this simple label that come from another previous work, in which basically, let's say, the value of the qubit is classical in superposition plus top and bottom. So the idea is there if you simply use partition, so you simply represent the relation of separability. Here you create a superposition. With the C0 you create the Bell state, and you arrive here, you don't know anymore, you don't know nothing. But with the indirect inseparability information, you basically have this adding information, so you know that these are entangled, but there are also direct inseparability. So if you add another C0, you are able to know that now P is a classical value, so it's separable from the other. That is the idea. Okay, I mean, in this case it's easy because you apply it to C naught, so they nullify by itself, but it works, I mean, it depends on the circuit, but it works also with more complex example. But it's not more like the understanding, it's more like abstracting the state than understanding if there are like specular operations that nullify by themselves.
Any further questions?
Yeah, so you don't have a static analyzer yet, but maybe you already tried to see if your abstract domain works well of standard quantum program gates, and how you did this kind of study thing. How accurately can you represent some quantum gates with this abstraction?
Yes, I mean, we are defining a static analysis now. And yeah, basically, we add more label here because we need more label to add more position. And yeah, what we have done, we have taken for now the set of minimal gate. So Hadamard, the gate, the set of Clifford gates. So Hadamard, Clifford gate plus T. So Hadamard, C naught, T and S. And we have built the abstract semantic of this 4 gate that is there enough to represent all the computation. And yeah, in order to have the abstract semantics on the domain, in order to do static analysis the classical way, we can say, like do the abstract execution of the program and obtaining this information in every point of the program and then use it.
So if there's any urgent last questions, I think we would have time for one more. But I guess not, so then let's thank Nicola again.